Our present our presentation is on HiCLIP, which is a contrastive language image pre-training with hierarchy aware attention. We're group 8. I'm Andrew, this is Sia. Online joining us is Nick, Ananta, and Abdul Rahman. So the intuition for HiCLIP is that hierarchies exist naturally in images and text. Things like grammar have hierarchies in them. CLIP is not able to understand these hierarchical relationships. HiCLIP is designed with the intent of learning these relationships, and it allows it to perform better on downstream tasks like classification. To train it doesn't require any additional labeled data. It's the same type of data that you'd use for CLIP. Directly learns a hierarchy from the raw image text pair. It's inspired by NLP tree transformers, which automatically find the hierarchies in text. So the tree transformer is being used in this model, and it merges the tokens for the text. The group transformer is what's used for the images, and it merges the patches for those. Once they're merged, they can't be split in later layers. And the merges are performed by an attention mask, which they call C. C is then included in the traditional attention scoring equation. Here, so at the top, this is the normal softmax equation that's used for attention. And then below that, this is the hierarchy attention version. As you can see, C is dot product with the softmax here and then multiplied by value.
Press the key.
Okay. So here's a diagram. This half is going to be the text. So the text goes into this tree transformer, and then we're starting at layer 0. It's going to find the neighbors that it has high affinity for. As you can see here, it decides that these are not a good match. And then layer 1, it'll find more relationships, and then layer 2, the same. So like traffic and lights are very closely related, whereas lights and sitting are not related in this this layer. Then for the images, that goes through a group transformer. And the idea is pretty similar. As you can see here, they start saying like, oh, these patches are pretty similar. It's a traffic light. This is sky. And then as it goes, the patches grow. So this is a visualization of what the text hierarchy will look like. So like these would be layer 0 mergings, and that's going to be merged with other text at higher layers. Eventually, everything is under one tree. Here's a closer look at the merging of the image patches. So as it goes, it makes more and more merges, and they can't be undone in later layers.
Right. So I'm going to cover the intuitive part of the hierarchy aware attention, which is the computation of the hierarchy mask. So first step is you're going to compute neighboring attention scores for any given pair of neighbors. So so it's similar to attention. You got to get the query and keys by multiplying a weight matrix, and then you could divide it by a scaling factor, and you would get a neighboring attention score. And this can only be done with neighboring tokens. So yeah. What's going on with the? I think the formatting of the slides went off. So the next step would be to compute softmax for each token. So the way you do it is you get the neighboring attention scores that you computed before, and then you get a softmax. So for each neighbor, it's going to be like a neighbor to your left and your neighbor to your right. And Lastly, you're going to compute the affinity scores, which is basically just a geometric mean using the softmax you computed in the previous step. Yeah. And most importantly, to prevent clusters from splitting in subsequent layers as you go up the loop transformer or the tree transformer, you want to make sure the affinity values are always higher in subsequent layers. So the mathematical intuition would be to have these affinity values be higher in subsequent layers. So the way you enforce it is you perform a weighted sum. So you have the affinity value from the previous layer, and you have the affinity value you computed in your current layer, and then you multiply it by a coefficient, which is also the affinity value of the previous layer, offset by 1. And lastly, you have the elements of the hierarchy mask, which is called the tendency to merge for each row I and column J. So the way it works is for any given pair of tokens, regardless of whether they're neighbors or not, it could be super far or super close. So what you do is you compute this value by chaining like affinity multiplications until you get it. So lastly, I'm going to show an example of how you compute a hierarchy mask for 3 token text. So we got Rick and Morty right here. First things first, you compute the neighboring attention scores S01, 10 to 1, 12. Next, you're going to compute the softmaxes for each word, Rick and Morty. Notice that at the edge, some of these values are like 0 and 1 because there's no neighbor to the left of Rick and there's no neighbor to the right of Morty, so it's going to be 0 and 1 automatically. Next, you're going to compute the neighboring affinity scores using the geometric mean, using the softmaxes you computed. And most importantly, you got to make sure these affinity scores are higher in subsequent layers by using the score from the previous layer, doing a weighted sum. And lastly, you got a hierarchy mask. So notice how the diagonals are all ones, and this is actually a symmetric matrix. So the values are same on either triangles. And I want to highlight the computation of the tendency to merge for Rick and Morty in this column right here. So like I said, you got a chain multiplication. So you got A01 to A12 since Rick is 0 and Morty is 2. So yeah, 0, 1, 1, 2, and you get the value. Now that we've covered the case of text and tree transformer, we're going to cover the case of images in the group transformer. So in text, you have only one dimension. That means you only have like 1 or 2 neighbors. So it's either left or right. In the case of images, it's going to be slightly more complicated. You're going to have up to 4 neighbors. So if you're a corner patch like this one, you're going to have 2 neighbors. If you're at the sides, you're going to have 3 neighbors. If you're in the middle, you're going to have neighbors up, down, left, and right. So we're going to make some minor adjustments to our formula in the case of text to images. So yeah, first things first, you got to compute the neighboring attention scores. So depending on the number of neighbors you have, you got to compute it for all of them. So yeah, up, down, left, and right, depending on where your patch is located. Next is the softmax values. So now the only difference between text and patches is you're going to have 4 neighbors at max. So you're going to have 4 values for 4 neighbors. So if there's no neighbor in any given direction, say you're a patch in the top left corner of an image, you only have 2 neighbors, so you don't have a neighbor on top of you or to your left. So those softmax values are going to be 0. Lastly, we're going to compute the affinity scores between any given neighboring patches. The formulation hasn't changed. You just compute it by using a geometric mean like this. And most importantly, you got to make sure the affinity values are higher in subsequent layers by enforcing a weighted sum, just like the case of text. And yeah, pretty much covers it for images. And yeah, last but not least, you got to get the tendency to merge for any given pair of patches. But the only difference right now is in text, you only have one direction. It's either going left or going right. In the case of images, you can go up, down, left, and right. So to compute a tendency to merge, we consider two paths. So the first one is we chain affinity multiplications vertically and horizontally. The other one is we chain it horizontally and vertically. Then whichever value is the highest one gets assigned a tendency to merge. And that's the case of computing hierarchy masks for images. And now we're going to cover the experimental settings, which is our training configuration and some evaluation metrics, as well as some ablation studies. So for the training data set, we're going to use YFCC 15 million, as well as a custom 30 million data set, which is basically YFCC 15 million combined with CC 3 million and CC 12 million. And to ensure our comparison is fair, every other model that we're comparing against is also trained on these data sets. So we're not using like original clip, which is trained on 400 million image text pairs, no. So when it comes to the downstream data sets, we're going to use 11 of them, and then we're going to perform zero-shot classification on them. And obviously, you're going to have ImageNet, which is pretty popular. We have C10, C100, Stanford Cars, Caltech, Flowers 102, etc., etc. So when it comes to training, obviously the vision encoder for our HiCLIP is going to be a group transformer. The text encoder is going to be a tree transformer. Image size is standardized to 224 to 224, and input text is always padded to 77. And the embedding size for the embeddings for both group and tree transformers is going to be fixed at 512. And as for training, not just HiCLIP, for clip, slip, and Philip, the hyperparameters are going to be constant. We're going to train it for like 32 epochs for all of them. And the scaling factor for the hierarchy-aware attention, if you guys recall attention, you got to divide it by a scaling factor. We're going to set it to 256. So now we're going to look at the zero-shot classification performance. Overall, HiCLIP outperforms all of them with the overall HiCLIP outperforms all of them with the exception of some anomalies in the C10 and C100 data sets. To be more precise, if you notice, these rows and columns, DCLIP and DPhilip, it's much higher than HiDCLIP for C10 and C100, as well as in the case of being trained on 30 million data sets, it's much higher for DCLIP. I must mention that DCLIP is not a clip model by itself. It's merely a different method of training clip. It's a self-supervised method of training clip. So in the case of HiCLIP, we just call it HiDCLIP. And now we're going to cover other tasks like text retrieval, image retrieval, visual question answering, as well as a visual entailment on the Stanford Natural Language data set. So overall, HiCLIP outperforms most of them. Yeah. If I recall, there's a few anomalies around here. Yeah, when it comes to text retrieval, image retrieval, all HiCLIP outperforms all of it on the recall metrics. And I want to clarify, R sum is basically the sum of all these columns for the retrieve in the case of retrieval. Yeah. And linear probe. So I wanna explain what linear probe is. So essentially, what linear probe is, it's a method of determining the quality of the embeddings from a visual encoder. So in this case, we're gonna determine the quality of the embeddings from clip and HiCLIP's visual encoders. So what's gonna happen is we take these visual encoders, freeze it, and we're gonna attach a classifier on it, train it, and evaluate it on all these data sets right here. So overall, HiCLIP outperforms all of them in classification. So it's kind of evident that the embeddings you get from the visual transformer from HiCLIP. It's much better quality than CLIP itself, with the exception of a few cases in the C10 and C100 dataset. Again, you can see how CLIP alone has a higher accuracy than HiCLIP by a slightly smaller margin, and these two rows, as well as only these two rows. Ablation studies. So now we're gonna make some comparison with the patch, some comparisons about the patch sizes in the training data set. I mean, obviously, if you train it on a larger data set, your accuracy is gonna be much higher. And if you use smaller patches in your vision encoder, your performance is also going to be higher. Okay. And lastly, I got to cover like the use of G transformer and group transformer and a T transformer. This is really important. So what the authors found out is that so if you look at these rows, this is HiCLIP basically using both group transformer and tree transformer. But I want to highlight using only one of these components. So if you notice, using tree transformer alone yields a much higher increase in performance as opposed to using group transformer alone. So this kind of implies that the language part of vision language models is really, really important if you wanna get a significant gain in performance. So yeah. And here we have the visualization of the embedding space using a dimensionality reduction technique called TSNE. So what happens is you have all these individual clusters. I want you to pay attention to the clusters. In CLIP, the clusters are all like merged together. So this kind of implies that CLIP has trouble determining which cluster and any given point belongs to. But when it comes to HiCLIP and DCLIP, you can observe that the clusters are much more well defined with like borders between them as opposed to this. And this is only done on training on a 15 million data set. Now, if we increase the size of the data set, the clusters become much more defined, regardless of whatever method you use, CLIP, HiCLIP, or DCLIP. So what this implies is that the scale of your data might determine how well your model performs. Limitations. So when it comes to the HiCLIP paper, the problem with that paper is they don't specify the architecture, the number of hierarchy aware hierarchical attention layers that it has in any given encoder block. Yeah. And secondly, the implementation is unavailable. We can't find a GitHub for it, so we can't do some test. We can't replicate these results that I just showed. Lastly, although HiCLIP introduces significant gain in performance, computing the hierarchy attention mask C adds on to a lot of overhead. There's a lot more computation. Yeah. So conclusion, if you introduce hierarchy-aware attention in CLIP in both the visual encoder and the text encoder, you're gonna have some significant gains in performance at the cost of more computation. And when the authors did mention they have a few future plans for HiCLIP, first one is to scale the visual encoder. They have this intuition where if you make it larger or deeper, that it might boost performance. And then they're gonna explore other methods of introducing hierarchy rather than a simple dot product that I just showed you guys before. There's a simple dot product that you do with a softmax. So we're gonna find other ways to do it. So lastly, you're gonna find like the authors did mention that they might consider introducing cross attention between the visual encoder and the text encoder to better form hierarchies based on multimodality. And last but not least, they did consider scaling up the training data set, because there's this intuition that once the data set size gets larger, the performance boosts that you get from HiCLIP might become redundant. Yeah.